Hey everybody, tonight we have a problem that deals with the ceiling function. So let's briefly review an example, a couple of examples here. The ceiling is the opposite of the floor function. So the ceiling of 8.6, okay, it's literally defined to be the next highest integer if you take a look at this definition. But notice, and this is sort of important the way this problem works out, that's equal to the ceiling of 9. And just like the floor function, the ceiling or the floor function of any integer is just going to be that integer. So let's write this down here. Equals, both of these values, both of these ceilings are equal to 9. Okay, and right here, you know, this would just be 9 minus 1 for both of them. See, 9 minus 1, and then 9 right here would be how this would be set up. And so the ceiling defines a range of real numbers. All the real numbers that are between c minus 1 and c have a ceiling of c. In this case, we're dealing with 9, okay? So let's take a look at how we might solve this problem that involves the ceiling of a square root function. And we are looking for a maximum natural number m such that this ceiling condition holds, okay? So now let's take a look at another truth before we move along. We do see a minus sign right here, and that gives us some insight into what this expression should look like to get a suitable answer here. The square root of something squared is just the something. Technically, it's the absolute value, I guess. But anyway, so the ceiling of the square root of an object squared is just that object, all right? So it's almost like the ceiling function is not doing anything at this point. But this is the structure that has to happen in order to, as far as I can tell, to find a solution to this. Now also, a minus b quantity squared, this is very well known, is equal to a squared minus 2ab plus b squared. So it makes quite a bit of sense to compare this part, the radicand, okay, this radicand, to this right-hand side of a minus b quantity squared. Okay, so let's do some analysis on that. Now, for this to have any kind of chance of working out, you would have to have minus 2 times a, okay? But 2 times a would be what? 4,048? 4,048? And again, y'all, we're just trying to force fit this thing. If it's going to work out, this has to be our savior right here, right? So in other words, 2 times 2024, this 2 and a. So our a would be 2024. 2 times 2024 is 4,048. Now let me go ahead and put times b here. Okay, like this. Now, it doesn't take too much work to determine that b has to be equal to 13 here, okay? Because it's just the prime factor. If you do this, division isn't particularly difficult. If you divide 4,048 into 52,624, you would get minus. Let me just write this out: 4,048 times 13, and that's not a hard calculation to do. Okay, but you see, in order for this to work and for us to figure out what our m has to be, this all would be the very same thing is 2024 squared minus this object right here, 4,048 times 13 plus 13 squared. This would be 13 squared right here, okay? And so folks, you see, we got what we wanted here. We just forced it to happen. If this hadn't worked out, then we'd be kind of stuck. But all we were given in the original problem is just this constant right here, right? And we had to figure out what the m is that will keep the floor at 2011. So we had no choice but to compare. Okay, and so when we that A has to be 2024 for it to work. 2 times the 2024 gives you this. Okay, and then you would have to divide. This is something you'd have to do manually, I guess. 4,048 divided into 52,624 turns out to be 13. All right, and then you get this expression right here. But what is that equal to? That's just equal to 2024 minus 13 quantity squared. Okay, but notice that the floor, or the ceiling, excuse me, the ceiling of this expression is just going to be the difference of these two numbers, okay, which is, so you see right here, I mean, that tells us exactly what M has to be, is what I'm trying to say. Okay, so this would, as far as this setup, the way we're setting this up right here, this would just be equal to 2011. Okay, and so the answer to the question, of course, is going to be M is equal to 13 squared. All right, M is equal to 13 squared. Let me get that. Hope this makes sense. Okay, M is equal to 13 squared is the answer. So M would be 2,000. Let me just write it up here. M is equal to 169. Okay. Now there may be something quite simpler than this that I'm overlooking. I think if you guys are familiar with this, you could just look at it and inspect it and probably figure out the answer. But to me, it made more sense to work with this established identity without having to do too much guessing, and just make the necessary substitutions. And then the only real arithmetic we had to do right here was divide 4,048 into 52,624. Okay, that produced this result, which produces this constant for M. Notice that if you were even one larger than this constant, let's say that if M were 170, that would make the ceiling be 2012. Okay, 168 would still give you a ceiling of 2011 if you imagine the square root of a very, very large number. Okay, between the squares, you're always going to have this floor or this ceiling of 2011. For example, if we tried 168, this would come out to be a decimal slightly less than 2011. Okay, which is very easy to believe once you establish this value right here. But if you picked, like, say 170, okay, that would push you just decimal points slightly above 2011, but that would mean a ceiling of 2012. Okay, so M equals 169 is definitely the maximum value that satisfies this condition, folks. And I don't doubt there's an easier way to do this, but this way worked, and let me know what you thought.